Hello guys, welcome back to our gas power analysis. We're gonna be working now on the gas diesel cycle, and this is our first problem. We're gonna analyze engine that has a compression ratio of 20 and which initial conditions are 95 kilopascal and 20 degrees. The maximum allowed temperature in the engine is 2200 Kelvin, and the thermal efficiency and the mean effective pressure is what we are looking for. So we're going to start by by drawing our TS and PV diagram. Remember that these are not intended to scale, but serve as a guide to have a better understanding of what is going on in our process. So we start with our PV diagram. We know we start with an isentropic compression. Then we have a constant pressure, heat addition, isentropic expansion, and then constant volume heat rejection. So these are our states. As for the TS, our constant isentropic compression, it's a vertical line. Sorry, this should be 2. Then we have our constant volume, constant pressure heat addition, isentropic expansion, and our constant volume heat rejection. So for this problem, we know that T1 is 293 Kelvin, since it's 20 degrees. P1 is 95 kilopascal. T3, which is our maximum temperature allowed in the cycle, is 2200 Kelvin. And please notice that we are asked to have constant specific heats. So that means 2 things. We're going to use our isentropic relations to correlate volume with the pressure and temperature. And second is that we will need to find out in tables. We can find a table A of 3, A2 and A3. The values of our specific heats. These values that I am providing are at 25 degrees, well actually 300 Kelvin. And we also know that our compression ratio is 20. What we are looking for is the efficiency and the mean effective pressure. So we start with finding our efficiency. Is the network divided by Q in, but from first law we know that work net is Q in minus Q out divided by Q in. And recalling our this analysis, we know that Q in equals H3 minus H2, which for ideal gas would be Cp T3 minus T2. Q out will be U4 minus U1. For ideal gas will be Cv T4 minus T1. Remember, Q in is difference of enthalpy since it's a constant pressure process. Q out is difference of internal energy since it's a constant volume process. So basically what we need to find out is these temperatures. As for the mean effective pressure, will be the net work, the net specific work divided by the difference of specific volumes. And taking account that R, which is a compression ratio, is V1 over V2, we can convert this to W net divided by V1 1 minus 1 over R. So we only need to find out V1, and V1 will come from our ideal gas, which is R T1 P1, which is the state because we know all the information already. Okay, so basically what we need to get is temperatures to compute our heat. We know T3 and T1, so we can start by computing using our isentropic relations in the process 1 to 2, which is our isentropic compression, we have T1 over T2 is equal to V2 over V1. So we can solve for T2. This will be T1 times, notice that we need to flip, so we will be V1 over V2. We don't have the values, but we know R. Now substituting, this will tell me T2 will be T1, which is 293 times 20 to the 1.4 minus 1, and T2 is 971.1 Kelvin. Now process 3 to 4 is also isentropic, is our isentropic expansion. So we can start by saying that T4 over T3 equals V3 over V4 k minus 1. But we know V1 and V2, at least we know the relationship because we know the compression ratio, but we don't know the relation between 2 and 3, so we will need to find out. We know that for ideal gas, process 2 to 3 is a constant pressure, so P2 equal P3, and if we invoke ideal gas, that will mean RT2 over V2 equals RT3 over V3. Since the gas constant is that constant, we can cancel and we can solve for V3 over V2. So at the end we're going to have V3 over V2 equal T3 over T2. It doesn't look like we have gained so much, but if we solve for V3, it will be V2 times T3 over T2. Again, doesn't look like we have gained so much, but recall that V2 and V1 are related with the compression ratio. So we can here say that V2 is equal to V1 over R. So we can substitute that here, and that will be V1 over R times T3 over T2. And now we have V3. So we can use this relation as V3 and we can substitute it here. So we have T4 over T3 will be V3, which will be V1 over R times T3 over T2, and we still need to divide by V4, this volume 4. Okay, minus 1. But V1 and V4 is the same. So we have cancelled this, and we can solve for T4 now, which will be 1 over R times T3 over T2 all of this times T3. In the next page we're going to keep this. So T4 will be T3, which we know, 2200 times 1 over R, it's 120, times T3, 2200 divided by T2, which is 971.1. We know K, which is 1.4. So this gives us 920.59 Kelvin. So we are ready to get our Q in or Q out. So Q in, remember difference of enthalpies, so will be 1.05 times T3 2200 minus T2 then 35.0, this is kilojoules per kilogram, minus Q out again kilojoules per kilogram, and this is our network. So 184.4 kilojoules. With this we can compute our efficiency, which is the first thing that we can get. 784.4 divided by 1035 gives us 0.63. If we multiply times 100, we get it in percentage, so the efficiency is 63.5%. Now for the mean effective pressure, we recall that we need V1. We can get it just by substituting the appropriate values, 0.287 times T1, 293, I guess, yes. Divided by P1, which is 95. So we have 0.885 meters cubed per kilogram. So that's our specific heat and specific volume. And so that means our mean effective pressure sorry about that. Our mean effective pressure is our network, 784.4 divided by V1, which we already have, it is 0.885 times 1 minus 1 over 20, and this gives us 932.2 kilopascal. So mean effective pressure, it's equal to 932.2 kilopascal. Okay guys, this is all for this problem. Next we're going to solve a second problem for a diesel engine. Okay guys, take care.